Okay, this is Mrs. A here with another polynomial experience. So far, we talked about polynomials and how they help us describe and understand that messy world around us. We talked about how we can better understand polynomials by looking at their degree, their terms, the leading coefficient, the discriminant. We looked at ways to solve a polynomial. We looked at the quadratic formula, identities, square root method, completing the square, and we looked at factoring. Then we moved on to what does a polynomial look like? What type of information can we get from it if we look at its shape and its form? And we went into the standard form for a quadratic and looked at its graph. And you remember its shape is a parabola that faces upward if a, the leading coefficient, is greater than 0, and faces downward if a is less than 0. Now remember, if a is 0, a cannot equal 0, because if a is 0, well then this is just a linear equation because the x squared gets canceled out. What we love about the form of a quadratic function is we see that U-shaped, and we see how the domain, it goes from negative infinity all the way out to positive infinity. But the range, it's limited either on the maximum or the minimum side of the parabola. So for example, for this downward facing parabola, the range goes from negative infinity all the way up to the vertex. And if we were working with an upward facing parabola, the same would go. We would again have a range that was limited at the bottom side, and then it would go all the way up to positive infinity. So looking at the parabola, we can see how there's this max or this min, and that could probably give us some great information about the function. So we put in an x value. Out of it, we can determine what is that maximum value by looking at that curve. And then what else we learned is that there's actually a form for determining what that point is. And it's called the vertex form. And, if you look, I'm going to turn on that. Look really carefully. Right now the graph is red, and if I click on the vertex form, it's blue. Well, the vertex form is a times x minus h squared plus k. And it's an identical function. It's an identity to the standard form, but it's put into a structure that gives us information about where the vertex is located. So the vertex is located from this form, we can see the vertex is located at h and k. And if I click on that, the label, you can see actually where the vertex is. It's also good to know that the line of symmetry, there we go, which is, it goes across that h. X is equal to h, that line, that's the line of symmetry. But again, that vertex hk, again, that's going to show us, for this parabola, it's going to show us the minimum and the maximum if the vertex is facing downward. Now, you know already, if you know me and you've been listening to my videos, I know that I can get to the vertex form by doing the completing the square method. But that's a lot of work. It's not always efficient, and it can introduce error if we're not really careful. And so what I love is there's also a way to calculate. If we're given the equation in standard form, there is a way, as long as we memorize it, to calculate the vertex directly from the standard form, and that is negative b over 2a. That gives us the x value for the vertex, and the y can be calculated by putting negative b 2a into the function itself as the x value. And again, doing this approach, if you look carefully, you see the vertex is in black, And if I click on it, this approach, it's in orange. And again, it's the same exact identical answer. It's just a different way of skinning the quadratic equation to get there. And for me, it's the way I like. Okay, so let's go back to the problem. So what we're going to work on today, I'm so excited about, is that we're going to look at applications of these polynomials. And we're going to look at how polynomials can help us solve the problems all around us, right in our own lives. And that's why I love this problem. It's a puppy problem about creating a pen. So let's jump in. You have just bought a puppy and want a fence in the area in the backyard for her. You buy 100 linear feet of fence from Home Depot and have decided to make a rectangular fenced-in area using the back of your house as one side. Determine the dimensions of the rectangular pen that will maximize the area in which your puppy may roam. What is this maximum area of the rectangular pen? All right, so we know that Polya's first step is always, can we state this problem in our own terms? And again, you can't see my eyes right now, but I'm not looking at the problem. I'm just trying to see if I can make sense of it. And there's a lot of words here, but what I got out of this is I've got 100 feet of fence wire, and I'm going to create a fence off the back of my house. And obviously this is my puppy, and I want that puppy to have the most area that it can run around in. So let's give this a try. So we're going to jump into our form, and the best way I think I would describe it is through pictures. And this is a very visual problem. So if I was going to describe this, we have 100 feet of wire. We have a backyard wall. That's my house. And I didn't see or read any constraints associated with the house. So I don't think the house itself limits the dimensions of our pen, only the amount of wire that we have. Okay, and then we're going to take that wire and we're going to put it across the back of our pen. So it says it's rectangular. Now remember, a square is a rectangle. So just because right now it looks like a rectangle, this could be longer than it is, wider than it is, and it could be a square as well. And so pause for a second and think, can you make this into a simpler problem? Do you see anything that reminds you of anything you might have done in elementary school that'd be an easy way to solve this? Put the video on pause and think about it and come back. Okay, so when I look at this, I mean, obviously I can take this and simplify it by reducing the wire length and making a table and trying to look for some relationship between the three sides to maximize the area. But I think one of the first things I noticed is I remember doing something like that then when I was in elementary school. Do you remember we were given the same problem, except it was for four sides. So it was to take that wire and turn it into I'm going to try that square again. Let's see if we can make a nice square. There we go. But this time we take the 100 feet and make it into four sides. And we tried this in many different ways when we were in elementary school, and we learned that there was actually a theorem, and it was that the maximum area given a perimeter for any quadrilateral is actually always going to be a square. Isn't it interesting? Now, the only thing is, though, that was when we were using the wire for the four sides. I have no theorem that says that applies for three sides, but that is definitely sticking in my head. Is this just a square? So let's jump in and try to understand this problem a little bit more. So what do I notice? The first thing I notice is that one solution could definitely be that this is a square. That's one thing that's sticking that I notice when I look at this problem. And I'm going to definitely want to examine that. And in that case, the three sides would be 33 1/3. and this would be the same. So the area would equal to side squared. So that would be, let me just do some quick mental math here to get an idea of what the area would be in this situation. So we would have 100 over 3 squared, which would be 10,000 over 3. 3 goes into 10,000, that's the repeating ones. So that would be 1,111 square feet, or we could say feet squared. That would be the area if this was a square. Now, I have to decide what I want to do with that. But that's one way of looking at this. And another is to, just think about how we've already worked with geometry. And, again, this may or may not be, well, we could do a better job there. Let's stick with some straight lines. Do that. Make a line there. And a line. Okay, it's a little bit like a trapezoid, but I think you get the idea that that's a rectangular shape that may or may not be a square, and that we would get the area by length and width to calculate the area. And so we have to plan now. What do we want to do? And we have a basic understanding. I would say, looking at this from a difficulty perspective, I cannot say that I totally got it at this point. But I also wouldn't say there's danger or any big rabbit holes. I don't think that there's any missing information. I really just think that this is going to need some careful planning, and we can easily do that. All right, so let's jump in. So the first thing to plan it. Now, when I'm thinking about planning it, the first thing I'm thinking of is thinking about heuristics, but in this case, I'm just thinking of my list of methods and how might I solve it. I mean, I could act out the problem. I could go down to Home Depot and buy some wire and act this out, but I don't think I want to do that. I drew a picture, and, that doesn't solve it, but at least gave me a better understanding of the problem. Could use a number line, make a list or a table, definitely, but I think I would be here for a while, and I just want to see if there's better ways. I could eliminate possibilities, solve a smaller version of the problem. I could examine a guess. I could go down that the square, and I could look at something larger and smaller and examine it, and that's something I'm going to consider. Oops. Let's go over here. That's something I'm going to consider doing, but I think also what I'd like to do is, let's back, examine a guess. It's up here. But what I think I want to do, knowing that we're working with polynomials and equations and we're in algebra now, I think I'd like to see if I can build an equation that can describe this problem and help me solve it. And I might go back to examine a guess. But I'm really curious to see if algebra can help me and where polynomials may or may not play a role in this. Okay, so let's jump in. So we said we're going to, we're going to use as our first try, we're going to build an equation. Now, to build an equation, how would we go about that? So we have our diagram over here, and to build an equation we probably want to look at getting those variables instead of having two variables, we want to use substitution to get that to one variable. And this is definitely doable by let's use purple. So if we put the W in terms of L, we would do W is equal to, so remember we've got both of these sides are L. So W would equal to 100, because that's the length of the wire, minus 2L. We could do the same thing for the L as well. L in terms of W would equal to 100 minus W, and since there's two L's, we would divide that amount in half. So we can either write this in terms of length or in width. I personally like length because I don't have to deal with the fractional components. I don't know if that sounds silly, but I like to avoid hard work. And if I can deal with integers instead of fractions, I'm going to choose that path. So let's give this a try. So the area we know is equal to length times width. And if we were going to write this in terms of length, then this would be a function, and it would be calculating area in consideration of length, and that would equal to, so length would stay, and W would get, the width would get substituted with 100 minus 2L. So do you see what I did there? I used substitution so that I have only one variable on the right side and I have my function A. So if I have a length, I can determine the area. And let's see if we can simplify this further. So we would have area of L is equal to 100L minus 2L squared. Okay, I think I'm definitely liking this approach because look at what we have. This is, can you guys tell me, what is this? Yeah, it's a quadratic, and we just talked about actually how quadratics can help us find maximum and minimums. So I'm wondering now, is this actually a good approach that's going to help us get there? I'm not fully sure I see it yet, but let's first put this in standard form. So AL is equal to negative 2L squared. This is a quadratic graph that would face, a parabola that would face downward, plus 100L. Okay, let's see. So now what are we going to do? So let's think about what we were just talking about with quadratics. We said that we drew a little graph over here. And we said that if we had a quadratic equation and the leading coefficient was a negative, that this parabola would face downward. So let's just draw a little picture to help us think this out. And I don't know that it's going to intersect like I just drew that. In fact, let's move it over a little just so that we don't confuse ourselves. We don't exactly know where that vertex is going to fall, but let me just put a little dot where that vertex would be, right there. Now, what is this saying? So let's just finish out our graph because you should never have a graph that's not labeled, right? And so here's our y, there's our x. The x is representing area. And, ooh, that's not true. Let's try that again. The x is representing length. So I'm giving that, putting that into the function for area. So y is representing area. Let me write that sideways. Area. Okay, so if I have a length and I put in, so as I'm going from left to right, I can see that as the x increases, y is increasing, or the area is increasing. So as my length increases, the area increases up to a certain point, and then it starts to go down. So all I want to do is get to that vertex, and that should give me the maximum if everything works out. Now, how do I get that vertex again? We talked about there's two ways, and that first way is we could take this equation and we could write it in. Do you remember what we were saying earlier? What could we do? We could use that method. We could use completing the square, but Mrs. A is not a fan. She loves to use it only when she has to because it's not always as efficient and can affect our accuracy. Now, but that would get us to vertex form, and that would help us quickly determine what that vertex is. But remember, there's the second approach, and as long as we memorize that formula for the vertex to go directly from standard form, And do you remember what it was? So the vertex would be negative b over 2a. So that would be the length, and the y variable, which would be the area, would be putting that x value into the function itself for the area, 2a. And we need a closing parenthesis there. So I think we have our two equations that we need to solve this. So let's move on to the try it stage, and let's take these equations along with us. So I love Notability. I love that I can just quickly do this. Let's do copy and paste. And let's do the same thing for the vertex. Let's just do copy and paste. And let's jump in and let's substitute the values and see what we get. So for the vertex, for the length, we're going to put in negative b, which is, let's see, I'm going to say that negative b is negative 100 over 2a, which is negative 2. So this is going to equal to 25. Do you see how I got to 25? If we got on the denominator, there's 2 times negative 2, which would give us negative 4. If we factor out the negatives, that cancel out. And then we can factor the 4 out of 100, we get 25. And that's how I got the 25. So again, remember what that 25 is representing. That's the x of the vertex. And if we look at what x is for the vertex, it's the length. So when I plug in this length of 25, that should give me the maximum area. All right, so that's our length. Let's just make sure that we remember that's length. And let's plug it in for area. So we would have a 25. Do you see what I'm doing? I'm filling in this y area here. So the function, and all I do is put in that value in. So a sub 25 is going to get me to the maximum area, 25 plus 100 times 25. That is equal to negative 50 plus 2,500. Let's make sure I did this right. 100, 25, and then negative 2 times 25, 100 times 20. Oh, when I brought this over, I apologize. I lost the L squared. All right, then we didn't lose a lot of work. Let's just take a step back. And do you see what I did when I copied it over? We had to be much more careful than I was. That should be 25 squared. That changes the problem a little bit, doesn't it? All right, so we have negative 2. And that's going to be, do you remember our perfect squares? 25 squared is 625 plus 100 times 25, which is 2,500. This is equal to negative 1,250 plus 2,500. And that's going to equal to 1,250. That is our answer, and that's in feet squared. So that's our area. And so we have our length, we have our area, and last but not least, we have the width. And the width is going to be equal to, see if we go back up here, 100 minus 2L. So we have 100 minus 2L, and our width is going to equal to 25 times 2 is negative, so that's going to equal to 50. And that's going to be 50 feet. And that's our width. And this is 25 feet. We can never forget our units, otherwise we don't really have an answer, do we? Okay, so does my answer hold water? One of the first things I'm thinking about is back to my square answer. The square itself was showing 1,111 feet, and I got an answer of 1,250. So my square approach definitely did not work. So that theorem that we learned in elementary school only applies for four-sided objects where the perimeter is not constrained by three sides but by four sides, and it doesn't apply if we're only using that perimeter to cover the three sides. So that's an interesting thing. Actually, it makes me wonder, like, I would probably want to examine that in Desmos a little bit and see why and what the relationship is between the two. Why square isn't the maximum for this problem, but it is if I use the wire for all four sides. That's something I'm going to wonder about. And I could definitely check quickly to see is this answer, does it hold water? I've already checked. It definitely does if I compare it against the square. I could, quickly create a little table and let's see. Actually, let's use black and we have length, we have width, we have area. Let's go a little bit larger. So if the length was, let's say 30, and let's see, if the length was 30, and so it would be 30, 60, and then the W would be, the width would be 40, then the area would be 1,200, and that's less than 1,250. What if I go the other direction? What if I increase the width? So the width is 50. Let's make the width 60. And then that would leave us 40, so that would make the length 20. And again, that gets us to 1,200. So I'm feeling pretty good that this holds water. And I feel really good about my answer. What worked, what didn't work? I'm definitely glad that I explored the square because I don't want to just ignore everything that I've learned. I want to be able to build upon it. And this helped me understand that the maximum area of a perimeter is always a square, provided that all four sides are using that perimeter, and that I can actually go and use this polynomial quadratic approach to solve maximum area for other shapes and sizes and perimeter constraints. So I like my approach. Everything worked nicely, and I would actually go off and give myself one of my stickers to say, great work, that I did fabulous. And that always just makes, these stickers just always make me so happy and keep me remembering that we really have to celebrate all of the hard work that we do. And there we go, paste image. And there we go. All right, so if you have any questions or comments, please feel free to leave a message on the YouTube site, and then I will look forward to meeting up on our next experience. I hope you have a great